Today I'll start off working out a simple problem on LEDs. The problem is that, as I mentioned before, gallium phosphide with zinc oxygen dopants are very commonly used for red emission at 6,900 angstroms. We know the band gap of gallium phosphide. We are told that the acceptor level, zinc acceptor level, is 40 MeV, the depth of 40 MeV, and the donor complex due to oxygen is 0.8 eV below the conduction band. So we have this is the oxygen complex, which is 0.8 eV. We have, this is the donor, this is the acceptor, this is 40 MeV. Band gap is 2.26. And the question is, what is the find average? Since I've given you just a broad emission wavelength, find the average donor acceptor distance. So emission is taking place, it's a donor acceptor transition which is giving rise to H nu, and we know that from this is Eg, H nu is equal to Eg minus Ed minus Ea, and there is the Coulomb attraction between the donor acceptor pair, which is notionally given by E squared by epsilon r epsilon 0 into whatever distance we want to find out, say r donor acceptor. But in MKS units there is a factor of 4 pi here. Otherwise you will get the relation completely wrong. So now if you use this expression, you will get the right values. H nu corresponds to 6,900 angstroms is lambda. Okay, so H nu is 1.24 by 0.69, so that is 1.797 eV is equal to 2.26 minus 0.8 minus 0.04 plus this factor. Okay, let's call this just say F. Okay, so this F from this comes to 0.38 eV. Okay, so this is the order of magnitude of this correction, just 0.38 eV. And now if you substitute into this expression, and I have taken epsilon r, what is the relative dielectric constant of gallium phosphide? Yeah, it's about 10. Actually it's 11.4, but I have taken, say, 10. Okay, and you put in all these values, E squared, etc., you get the right RDA comes out to 3.78 angstroms. Okay, this is in electron volts. Okay, so this E, you take out one E because the whole thing is in electron volts, and you see this is a realistic value, the donor acceptor. So this F, unless you take this value of 4 pi, you will get wrong results. And this is the same as in the case of ionic bonding. Okay, if you have worked out problems on ionic bonding, okay, so in order to calculate the attraction between positive and negative ions, it's the same. Okay, there you have Ze squared, okay, coming in. So it is very important in order to get correct values that you take care of the units. If you don't use the right units, you will get absurd values of F. F cannot be, few electron volts. It cannot be few electron volts. Okay. Okay. So this is an example of this donor acceptor pair recombination, and you can see that although the band gap is 2.26 of gallium phosphide, you are getting red emission due to this. Oxygen is the donor, this is the acceptor, and in this case you are getting red emission. As I mentioned last time, gallium phosphide is capable of, because it has a wide band gap, you can get the whole spectrum from green, yellow, orange, red. Okay. Now, I mentioned last time that blue is not readily obtainable with the materials I've discussed. So I'll just show this diagram. Which, can you see this? Can you just about see it? You can't see it. Okay. So I'll draw this diagram. Obviously, for blue, you need large band gap materials, and the band gap will span from, say, 1 to 2, 3, 4, 5, 6 eV. And from the periodic table, we know that we have to go to lighter elements. Lattice parameter going from, say, 3, 4, 5, 6 angstroms. And if I sketch this, find that some of the most important materials are. Okay, let me do this. This is aluminum nitride, and since gallium and aluminum have almost the same size, this is almost vertical. This is gallium nitride. Indium nitride has lower band gap and larger lattice parameter, about 3.5. So this will be about just about here. These are of the zinc blend variety. Okay, so you can have, this is a family of nitrides which spans a band gap from about 2 eV, 1.9 to 6. Okay. And these are all direct gap materials, so you can get solid solutions of indium gallium. But obviously here you have lattice mismatch problems. Aluminum nitride and indium nitride, gallium, these have slightly different lattice parameters, but you can span the entire range from 2 to 6 eV. And in fact, we are not interested in 2 eV because we already have gallium phosphide here. So we are really interested above this. Okay, we are interested probably in this region above 3 eV. So above 3 eV, we can have just a little bit of indium and gallium nitride, or this whole series. Okay, so these are the 3,5 nitrides which are important, and I'm emphasizing this because these are direct gaps, so they're at the basis of the new blue emitting laser materials. And the conventional 2,6 compounds have slightly lower band gaps, but they're nevertheless very useful. We have zinc sulfide, which a band gap of almost somewhere here. Okay, I'm drawing this rather. Zinc selenide is about somewhere here. Magnesium selenide is somewhere here. So you have a series, another series, zinc sulfide, magnesium selenide, magnesium sulfide, and zinc selenide. Okay. Now, it turns out that zinc selenide lattice matches with what? Cadmium selenide is here. Okay. The older ones, aluminium phosphide, gallium phosphide. Yeah. Okay. So gallium arsenide lattice matches with, so it is just somewhere here. Okay. This is gallium arsenide. The older 3,5 compounds, indium phosphide is somewhere is here. Okay. Aluminium arsenide is somewhere here. So one can grow because of this lattice. One can. This is almost vertical, so you can grow zinc selenide on gallium arsenide. And if you're wanting to go towards zinc selenide, is just less than 3 eV. So in order to get into the blue region, you have to alloy zinc selenide with either magnesium selenide or zinc sulfide, etc., to go into this region. Okay, which is. So these are the 2 6s, which are very useful for both LEDs and lasers in the shorter wavelength region. Okay, let me now talk about the device aspect of LEDs. LED is just a PN junction, which is forward biased. N is negative, P is positive. Okay, so holes are injected into the N-type region and electrons are injected into the P-type region. And since the light emission is due to recombination of electrons and of holes, one can say that the device efficiency from the electrical point of view at a 0 depends upon 3 factors: at a injection, at a recombination, and at a extraction. This is injection efficiency, recombination, and the extraction efficiency. It's the product of these 3. Because the process of light emission involves what is the injection of minority carriers, recombination, the electrons and holes, either directly or through impurities, and then the light has to be extracted. And as I discussed last time, there's a difference between gallium arsenide and gallium phosphide, because one substrate is transparent and the other is not. Now, from simple PN junction theory, we know what at the injection is just, suppose we're talking about injection of electrons. Suppose this is an N plus P junction, so we're interested in the injection of electrons here. So the injection efficiency is IN over total current, which is IN plus IP. And this, from the Shockley theory of PN junctions, is just dE NP0 by LE over dE. Diffusion coefficient of electrons, NP0, is the minority carrier concentration of electrons in the P region in equilibrium. LE is the diffusion length of electrons, and DH is the diffusion coefficient of holes in the N-type region. PN0 is the concentration of holes in the N-type region, and LH is the diffusion length. So if you just simplify that, we have the expression 1 plus DH LE PN0 over DE LH. I think this should be NP0, right? DE DH PN0 NP0. Okay. And this can be further simplified. 1 plus mu H PP0 LE over mu E NN0 LH, because we know that N0 into P0 is equal to Ni squared in equilibrium, and where PP0 is Na, we are assuming all the acceptors are ionized, and Nn0 is equal to Nd, full ionization. We want this factor to be as close to unity as possible, so obviously we want this to be negligible. And it turns out that we know that mu H is usually much less than mu N for most materials. Le is less than, is greater than or equal to, we can say it's equal to LH. Okay, so when Nd is much greater than Na, it's a N plus P junction, the injection efficiency tends to unity. This is the same as condition as in an N plus P diode, okay, or an NPN transistor. NPN transistor, we want the injection efficiency of electrons into the p-type region to be very large. In practice, what happens is that for gallium arsenide, where the mobilities are large, okay, eta injection is about 0.8. Gallium phosphide, the electron mobilities and the hole mobilities are not that large. Eta injection is of the order of about 0.6 to 0.8. We have seen different recombination processes. The recombination process is given by an efficiency for, say, for example, zinc oxygen in gallium phosphide is about 30%, and for nitrogen, depending upon where you are, if you are in the indirect range, okay, gallium phosphide, so it's in the indirect range, it is rather low. It's of the pure gallium phosphide. Remember, I showed that as you're going from gallium arsenide phosphide to gallium phosphide, the efficiency decreases, but it's much higher if you put nitrogen in. On the other hand, if you have double heterostructure LEDs, then due to carrier confinement, you can have efficiencies of about 60 to 80%. What is this double heterostructure LEDs? If you have as in the case of laser, you can have a okay. I'm just drawing this schematically. This is a thin active region which is nominally undoped. This could be N, this could be P. Okay. So in this region, okay, which is relatively narrow, say maybe 1,000 angstroms, okay, or less, you have both. This is EC, this is EV. You have a higher efficiency because you have carrier confinement. These barriers for electrons and holes are much, say delta EC could be something of the order of quite easily 0.4 to 0.5 electron volts, and this is much larger than KT. Okay, so the electrons cannot get out, and delta EV here is typically something like about 0.2 electron volts. Okay, so the whole electrons and holes are confined, and obviously the probability, recombination probability is increased, and you can get light emission. This is the same basic principle as a heterostructure laser, which I'll discuss in detail later on. Let's get into a little more detail about light emission from LEDs. We want to find out what is the transition probability, what is the recombination rate for a direct bandgap semiconductor. That is a conduction band, that is the valence band. This is E, this is K. Okay. Electrons and holes recombine, giving light H nu. Is we are assuming that this is band to band. So the electron, say energy E at a momentum value K dashed is say E2 for the hole. E in general it could be a different value of K dashed. The energy is E1. So E2 minus E1 is H nu. This is E2. This is E1. Is equal to H nu. This is equal to say E. And from the selection rule, we find that since the photon has 0 k vector in this scale, the selection rule gives that k dashed must be equal to k dashed double dashed is equal to k for high probability of electron hole recombination. Okay. So what is E for the hole? What is the EK relation? EK dashed is equal to, hole is here in the valence band, so it's minus h squared k dash squared by twice mh star, effective mass of the hole. E k double dash for the electron is Eg plus h squared k double dash squared over twice me star, and as we know me star is usually much less than mh star, and from this we find that k squared is equal to twice mr over h squared E minus Eg, where Mr star is the reduced effective mass, Me star Mh star over Me star plus Mh star. This is important when we are talking about the joint density of states. So this is a reduced mass. And near the bottom of the conduction band, we know that we've already written the relation for Ek double dash. We have E2 is Eg plus Mr star over Me star E minus Eg. This just follows from the this relation here. Okay. Now, emissional photon involves the density of states in both C and V bands, and we've already seen that conservation of this gives the conservation of energy and this gives the conservation of momentum, so these are involved. So we can define a joint density of states by the relation Ne2 dE2 is equal to Nje dE, and therefore Nje joint density of states is Mr star over Me star into N D2. Okay. So that is one relation we'll come back to. Now, from the elementary theory of semiconductors, we know what NEDE is. Variation of the density of states with energy goes as e to the power half from above the conduction band. So the exact relation is MC, where MC is the number of equivalent minima in the conduction band, MdE by h squared, 3 by 2. This is like NC. Okay, this is NC 2 pi m kt to the power 3 by 2. E minus EC to the power half dE, where MC is the number of equivalent minima in conduction band. Okay. For gallium arsenide or direct band gap semiconductors, this is just equal to 1. But for silicon or germanium, okay, silicon, there are 4 minima, equivalent minima. In case of germanium, 6 equivalent minima. But we're concerned with direct gap semiconductors, so MC is equal to 1. So using this and the previous relation, we have the joint density of states NJE is equal to twice Mr to the power 3 by 2. The substitution, E minus Eg to the power half. Units are electron per electron volt per centimeter cubed. This is for parabolic bands, remember, because I've assumed that E is proportional to k squared. We want to actually calculate the emission probability, the lifetime. So we know that the rate of spontaneous emission RSP function of energy is the emission probability into the joint density of states into the Fermi function for the conduction band into 1 minus the Fermi function for the valence band. We want electrons to be full and holes to be empty. It's per second per electron volt per centimeter cubed. What is the total spontaneous emission rate, RSP, per volume, is the integral of this over range of energies, and from this we find that we can calculate the emission probability, which P emission, which is nRQ squared epsilon PCV squared 1 plus UE over 3 pi epsilon 0 m squared 8 squared over c cubed. A lot of constants, but the important material parameters are PCV is the matrix element of the momentum operator, and this is equal to 0 unless K dashed is equal to K double dash. So this gives the selection rule. Okay. Okay. In this, you find that there is PCV comes in, and PCV is related to the oscillator the oscillator strength for this transition, for which numerical values are available. FCV is twice PCV squared by M0, which is 23 EV for gallium arsenide. What are the other terms that are NR is obviously the refractive index. The photon density per unit energy interval NP is equal to NE into UE, where UE is the number of photons per mode, which is equal to 1 for spontaneous emission. And the others are material constants. So if we take Fn, we can say that this is just EFN, and FP, the quasi-Fermi level for electrons, and FPE1 is just EFP, quasi-Fermi level for holes. Then it turns out that this relation, the value of PM For gallium arsenide, this is quite well known, so take that as an example. The emission probability turns out to be 1.8 into 10 to the power 9 per second. And so the inverse of the emission probability is the recombination lifetime, direct recombination lifetime, which is 1 by that, which turns out to be 0.6 nanoseconds. Okay. So this is the in good material, which is not very heavily doped, does not have a lot of defects. There are no non-radiative recombination centers. So the lifetime is of the order of about 0.9 nanoseconds. So this can be measured directly by having a pulsed source and looking at the decay. So what happens if you have suppose you have a pulsed laser, okay? So say light intensity as a function of time, and you switch the laser off, okay? Then the light intensity from the gallium arsenide will decay like that, okay? As e to the power minus t by tau, where this decay time will be of the order of 0.6 nanoseconds, okay? So one can actually measure this. This is assuming that the surface recombination is not very fast. It does not have a lot of non-radiative recombination centers and other defects. I just want to calculate the responsivity. Under injection conditions, we have the quasi-Fermi levels, but under thermal equilibrium, we have EFN is equal to EFP. There's only one Fermi level, EF. So Fn E2 into 1 minus Fp E1 is just the Boltzmann approximation, E exponential minus E over kBt. So then we can, if you put this in the expression for spontaneous emission, RSP epsilon is equal to twice mr star to the power 3 by 2 by 2 pi h cubed t r e minus eg to the power half e to the power minus e minus eg by kBt. For weak injection, when the Fermi level splitting is not very large, then we can rewrite that expression as twice mr star to the power 3 by 2 pi h cubed and here instead of E minus Eg we have EFN minus EFP, that's the Fermi level, quasi-Fermi level splitting, minus Eg over kBt into minus E minus Eg by kBt. Yeah. Here there is another term which I've missed out. This is e to the power minus Eg by kBt. So here there's e to the power minus Eg by kBt. So the total photon flux phi 0 is VL, the volume, active volume, integration over energy, RSP, and this turns out, if you substitute in e to the power, this is the important term, EFN minus EFP. So with high injection, this value increases because the Fermi level splitting increases over kBt per second. Okay. Where here TR is nothing but the inverse of the transition probability, and VL is the active volume. So if you look at the energy spectrum, this RSP E, what we've calculated is this spectrum. Okay. This is EG. Because on the average, the integration of this is obviously RSP, and why is that? Because remember, when we look at the semiconductor, this is the conduction band. Okay, the density of states goes, say, something like that. Valence band density of states goes something like that, and the actual carriers that are occupying the bands, and this is the maximum, which is typically half kBt. Okay. So recombination takes place not only from here to here, but obviously the density of electrons is here, maximum density of holes is here, maximum. Okay, so the maximum here is not at the band gap, but at slightly higher energy. And the responsivity, which I've defined before for detectors, responsivity for emitters is just R, the ratio of the power output to the current in, which is power output is the photon flux into the energy of each photon over I. And so this is eta 0 h nu by q, and we have a similar expression for detectors, 1.24, because h nu we know is 1.24 by lambda. Okay. So if lambda is in microns, the responsivity is given in watts per amp. Okay. So responsivity of a diode is similar expression, 1.24 eta 0, this is the quantum efficiency, okay, by lambda, in watts output over amps input. Whereas for a photodetector, it's the other way around. It's amps detected over watts incident.